wires here. Ah, you're not in it though.
Yeah. Is that a new one? Starting soon.
Are we good? You didn't get the. Oh, sorry. Last try. If this doesn't work, we're just gonna start.
So what are we doing?
Check your email one more time. And like leave the other hangout. Did you leave the other hangout?
Yeah, the other hangout is theirs. I think they're going.
Yeah, I think we're fine.
You're just not in it though.
Here he comes to save the day. Cool. All right. So no guarantees about how the lag on this thing is going to work or not work. So we good? Yeah. Tolerating. Yeah. So top thing started with analytics data engineer over at a startup called Billboards. Full times tonight. Have predictive analytics and data roles over 15 years. So I used to do this run company. Degree. It's quite cool, hands-on. It's right over there. So we're not going to discuss how to build Skynet. Now, if your company builds Skynet and wants to implement machine, but we're not going to. So, and I think the motivation for this talk is, you're working for a business. When would you actually use machine learning? And then let me get a show of hands. Who works for a business? Almost everyone. How many of you have implemented machine learning so far? 1, 2, 3. Okay, so. Huh?
That's supposed to be a strict subset. What if you don't work for a business?
No, it's not a strict subset. So yeah. But yeah, so this talk's going to be focused. It's going to be a business-focused talk. I think the motivation for me was I kept having a lot of time to implementing machine learning classes data, and it have a certain level of math knowledge. I mean, it's just cool. So now you know all these algorithms, and now a business, how do I make the jump from here probably to where that. Okay. Anyone else? Idea of what
Computers
machine-
building models.
Okay. So things that plays against is playing chess, and he got to play a world tournament, checkers. How well, buddy? There's been other definitions, like, you know, a computer that programmed that on its own without. This is basically Bill turning onto this Venn diagram here of you know, sets of knowledge. You know, do machine learning, data science. Being a programmer and having math knowledge. We're also going to here. So machine learning probably isn't applicable. So, a quick example from real life case. Years ago, I worked with one of the trends are actually 20 and turns. We're working with a it took several math PhDs to figure this out. So there's a guy with a hammer every that. Takes looking at the data. You know, with a fresh set of eyes. The answer's right in front of you, and the problem maybe. And right, so we're going to classify photos. matters, and we're going to get into this. Group discussion. Real life example here. A bit, so cool. So, okay. Which is problem of. Okay, so if classifying where there's high traffic areas, high number of impressions. So you'd think that all those things would be linearly correlated, right? Like high and improve, but there's billboards all across the board, no pun intended, where in high quality areas, you're still having to discount the billboards. In medium quality areas, they're getting more than they would in high quality areas, and low quality areas, and it's more than medium, and so forth. So it's a confounding problem because they're trying to forecast their revenue and trying to figure out like which attributes would help them sell more billboards at a rate that's going to obviously improve the margin. And so, some possible solutions they came back in with as well. Okay, you guys have a quasi-monopoly on all the billboards too, so why don't you just charge whatever you want? The problem is these billboards sit basically in just or whatever around. So charge whatever they want, but will the market demand it? Sorry, and then a short check. They want to try and maximize margins. So it's still, why is it that we have billboards in high traffic areas that we're having a discount, and why is it that in medium areas, we're able to charge higher rates? It's an interesting problem, and it's hard to forecast. So maybe linear regression model might be a good way to start out, right? You have yes.
So you have the billboard. There's a price you charge for it, and then you have the number of people that see it, and also just where it's located. Is that?
Yeah. So let me go through the variables real quick. Thanks. So you have location. So you could think of I-15 as being a very high traffic, very desirable area for billboards because that's where a lot of people drive. You have impressions, which are the number of people who see your billboard in a given time span. And that's really the metric that a lot of advertisers go off of. It's impressions drives what's called a CPM rate, cost per thousand. And from that, you can get an idea of how much you're going to charge for those impressions. The problem is that these two didn't seem to drive. And then weeks unoccupied, right? That's the number you want to reduce. So if I have a billboard that's out there for half the year, empty, it doesn't really help out. And historical negotiated rates.
This is taking into account the length of the impression.
No, it's eyeball. Exactly. Yeah. So if he's, an impression could just be I drove by the billboard actually and didn't look at it. Right. And so you got to understand too. A lot of the advertising is geared towards making your impression numbers look really big, so you can increase your CPM. So makes sense. Where there's like low impressions, unless it's high quality, but that's a different matter. So now let's implement a billboard forecast problem. So let's get really, really deep here. So let's go over a framework for implementing machine learning. So I think the first thing is really understand the problem you're trying to solve. It goes without saying, but you'd be surprised at how often people will jump into the the model design and God knows what else, without really trying to understand, what it is you're going. I laid out some basically BS numbers here for the amount of time in implementing machine learning. We'll just call this 20% of your time that's spent understanding the problem. You'll notice as you go down the line that machine learning and analysis, at least in my experience, is actually a pretty small fraction of the total amount of effort. So understand the problem you're trying to solve. I think all of you, most of you work in a business setting, and those who don't still have problems you're trying to understand. So, I mean, it really comes down to just, if you have more domain expertise, it's extremely helpful. It goes without saying, but again, I think you'd be surprised at non-domain experts trying to solve problems they don't understand. They can get to some pretty interesting conclusions. So, I mean, this falls in line with relationships too, right? Like if you're not a domain expert, maybe find somebody who is. So, and also this goes along with some other stuff we're going to find out. Like relationships, I found, in my predictive analytics career has actually been one of the more beneficial criteria is knowing the people who can help me get the data, knowing the people who can help me set up servers, or I set them up myself, but and just knowing who to talk to. Again, what does the customer or the end user expect? Getting data, it goes without saying. With machine learning, math is a pretty big deal. So how many people have taken a machine learning course online, just out of curiosity? So did any of you understand the math that was behind a lot, right? So I've heard this from other people too. We take a Coursera class, and the most popular one's machine learning class by Andering. So you get into that, and it goes into gradient descent within like the first few lectures, I think. And if you don't understand like partial derivatives, inverting matrices, and linear algebra and everything else in between, it becomes a bit opaque. I had people come to me like, well, this is great, but I don't understand any of this. So I mean, you can get through, and I think I have an intuitive understanding, and that goes a really long ways. But it does help to brush up on your math. I mean, you don't need to be an expert. I mean, I have a math degree, and I've probably forgotten most of what I learned because that's just how it is. But brushing up on what you need is extremely helpful. And it'll help you understand the scope of the problem better and the solution. The most important thing is to understand what done looks like, right? So we're going to solve this problem. What's the outcome? What do we expect to accomplish here? So,
Yeah.
I mean,
sure the client knows what done looks like.
Yeah. So, I mean, Bill and I are going through this right now at work. We're setting up the framework for analytics, basically all the infrastructure. So done is an ever-moving target, but at least if you can establish done for today, that's puts you in a much better spot. So, okay, so understanding the problem with the Billboards forecast problem. So I used to be a marketing analyst. So I actually dealt with Billboard, and they knew I understood the problem. So that was a pretty simple thing. Again, we'll take a stab at that.
Historical price, is that, so are we trying to predict new prices?
Yeah, off of the historical rates. Yeah, right. Just come up with a model that can, makes more sense. But
Would
exactly.
your problem be minimizing the vacancy and change over?
That's definitely one approach, yeah.
So done, you wouldn't know until time passes.
Exactly, and we'll get in a second. And it's a iterating process of problems like machine learning is tongue in cheek And one event because the case model they're listening to me doing something else. So what's up?
But yeah, Done's a moving target, but you need to you need to make it through those iterative steps,
Yep.
right? Like if you start out and you go, okay, I have all these locations, and then you immediately start to put traffic models on top of it and population predictions of like what's the population going to change for different areas. You might and trying to figure out what done is going to be. So it's really good to figure out what is like a minimum value product first, get through it first. And so that's I understand the linear regression. We're just going to plot a line and see what we should charge next week. And that's it.
It's basically it, right? I mean, yeah. And the notion is you'll see down the line. It's just start simple. I think that's like one of the emphasis too. Is you start simple. You can always work up in complexity. Working backwards is trickier. So,
as you add complexity, it turns out to not be worth it anyway.
Right. So yeah, now we're in the data phase, right? So a lot of your work's gonna be spent getting the data, cleaning and munging the data, converting the data. I mean, anybody who's worked in data, I think Fitz can attest to this. It's a slog. Yeah, and see, this is the hardest part. So, and most of the sorry.
Sorry. So what's the difference between converting and cleaning and munging?
We'll get into that in a second. Basically, the difference is converting means converting like machine readable form, so numbers. Cleaning the data is not doing that, and everything else. So, yeah, in the projects I've worked on, predictive analytics, the data has always been the biggest hurdle. So, I mean, if you're doing time series forecasting, for example, you gotta have sales. And you have to have proper time horizon buckets and so forth. And that's, in most business data, that's actually really tricky to get. So, let alone anything else you're trying to solve. So in this case, it was pretty simple. I got a spreadsheet and I made the numbers fake so you wouldn't be able to see the data. So let's see. Everyone's, that's a rhetorical question. You can't see that.
Shift Command Plus.
Yeah. Okay. So this is basically the first version of the data that I got. I massaged it a bit so you actually wouldn't be able to tell the real numbers because that would be bad. And I also truncated it to 100 rows for convenience sake. So anyway, this should highlight, I think you can just go down the list and kind of see the problem we're dealing with here.
There's 4 variables.
Yeah, 4 variables. So you have location quality, medium, high, and low, daily impressions, weeks unoccupied, and then I called this conveniently label to emphasize that you're going to have something to point to. It's also called revenue. But does this data make sense so far? Mm-hmm. Cool. And then made some stats. So just first thing I usually do is just understand the data that I'm dealing with. So and as a side, I'm actually a fan of Excel for smaller problems. So I know that's probably like Satan talking, but it works really well if you know how to use it. I mean, I hate to have to import files and do all this stuff. I can just do it in the spreadsheet itself. So I'm going to do a count on high, medium, low. Notice there aren't a lot of low examples, which we'll get to in a second. I try and correlate the numerical data against the label, just to get a rough approximation of how the features line up against what it is you're trying to predict. It's a good guideline. We can get to the details later, but not. But min, max, mean. It could also include median if you want, and standard deviation. So again, it's just trying to understand the base data that you're getting, so you can move on from there. And probably a more advanced approach, we'd do feature selection and whatnot, but we're not going to get at that here.
Plotting would be another good one.
Yeah, plotting.
So plot So you calculated the mean, but that sort of assumes that, well, I mean, that's the average. Mean is standard deviation, but
Yeah.
is it actually Gaussian? So plotting the histogram.
Yeah, and there's certain assumptions with linear regression, which I won't get into, but one of them is, you know, normal distribution and whatnot. So I mean, it's absolutely legit, and we'll show a plot of this data in a second. Okay, so now let's implement the forecast problem. Wait, we just went through here. Sorry. Okay, so Louisville data is pretty messy. So that's Will Ferrell, who's a janitor. So, you know, assuming you have lots of data sources, which you probably do in a business, especially if you're getting to the point where you want to do machine learning, you're going to run into these issues. Data sources, formatting, integrity, grain. But, you know, the bottom line is more data beats clever algorithms. So. I don't know who actually said that, but it's an adage in data science. Basically, you know, especially in the days of big data, you're making the assumptions that you know, you can overcome any problem by just throwing a lot of data at the problem.
So
Yeah, what's up?
I think what you're saying with those items before the last one is that more data is good, but you know what the quality of the data is.
That's exactly it, right? So when I say data, I assume that it's it has integrity, it has consistency. I should look it up. It's the data that you're looking for, right? So
if you don't know what your data means, then it's practically useless.
Mhm.
Right?
Yep. And that's definitely one of the central points I'm trying to make is that the businesses have a lot of data. They generate a lot of data, but what's useful for solving the problem? So something to think about. Some data will mislead you. So, you know, a classic example are what we called ringers. So in this data here on the bottom, can everyone see that okay? Cool. So you're assuming that in the data set, all women are pregnant, and that's going to be your label that you're trying to predict against. Now you have another feature called gender. If you have two males and females, do you necessarily need that label? Do you need that feature to inform? Yeah, you're trying to predict if somebody is pregnant. The data females, but and then some feature in there. And so and they would punch in the data and get back a prediction. We trained like the form, right? So it contained actually the most of the data was actually all the credit history. So it was all retroactive data. So you really couldn't use it at all. That's all we need to know. We don't need to know if they bailed or didn't pay. So now, when you're training against it, now useful. So, yeah. We're going to be getting. You don't know how accurate your start getting wacky. You start stuff like these, and unfortunately, days later. Right. So you want to predict on. So let's talk about this. Okay. So how would you predict what is a chair? There's no developing like you know, right? Yeah.
The image in the chair?
Yeah.
Maybe. Okay.
Images of chairs.
The hand really hard.
Right. So I mean, you know, this is
your outlier.
it's not a trivial. Yeah. Right. So again, you know, the more data.
The color. Misleading, right?
Right.
Like, you models, but including everything that fiction is.
Yeah.
It only works on like famous works of art. It tells me what my images are. And when I was in DC, it got everything right.
Right.
I knew where I was. Every other time I take a picture, and I just took a picture of a magazine cover, and I was like, that's the movie Wolf.
I've actually,
That's awesome.
I've noticed it can actually identify jet airplanes really well.
And it does pretty well with flowers in it too.
Yeah.
Okay.
I was at Boeing Field and it was like, oh, that's a 777. I was like, that's pretty
Probably
good.
just people who are interested in that specific type of data, right, putting it in.
What was the name of that?
Google goggles.
Google goggles.
Lots of feedback from people.
Sure.
Yeah.
Whether
Right, and these are you know.
Right or wrong, and that's exactly how Google works.
Yeah.
Why they're so big.
Yeah, I mean,
And they help, and there's a lot of people that do that sort of thing. Get information from, feedback from like tons of users. That's actually the best way to get data.
Right.
Translation, lots of things that they get people to tell you what the answer is.
Yeah.
And they'll correct it, and then once it's corrected, Google tracks that.
Yeah, it's a beautiful example. I mean, and they still can't get this right sometimes. So, so it wasn't a trick question 6. Can you guys please figure this out right now? I mean, it's more, you know, this Google does this every day, not just everything. They
You do it. Like you could easily go, oh yeah, all of those are chairs. And if you threw in a table, you go, that's not a chair. But the trick is trying to get a computer to do it.
Right.
And trying to get it to figure out, oh, that hand is actually a chair. Which is where the model comes in.
Yeah. Well, Dylan brought some attention to those. Now we're time to do some machine learning, I guess. So, start simple. So I put down, but in a real business setting, your resources are very limited. So you can do this all day. But it's not. Really going to get theme here. Simple, have a training set and a test set. Training set is what you're going to train your model against, and your test set is what you're going to validate your model against. So the tip, you're just doing training and testing. Here, it's not is so rule number one examples should be a mini data to have distribution of examples proportionate to the examples. That makes sense. And then another rule is don't test on your training data. So once you fit your model to your training data, don't go back and try and test on it because that's cheating. And you'll be really wrong. So the paradigm that you want to think of is you want to fit a model, you want to predict against a test set, and then assess the accuracy of your model. Right, and this is a constant iteration. And so that makes sense, everyone? Cool. Okay, so let's look at some code. Probably not see that okay. Won't see that okay? One or two more? One more? Okay. Okay, so in this example here, I mean, it's a very trivial example, but I think more we just want to go through the process of fit, predict, assess, right, and also loading your data. So in this case, we're going to use matplotlib, NumPy, and pandas. So these are all, and then sklearn down the block. These are all pretty standard libraries. I think you've all seen them before. So first thing is read the data in and take a look at it. So this should match what we have. Will make sense. We're stating the first values here. Weeks occupied against the label, which is revenue. So y-axis is revenue. So
Any
x-axis needs to be impressions here. Sorry, I know you can see that. So it needs to be the impressions and then the weeks unoccupied. So you can see there is a relationship. As impressions go up, you make more money. As weeks unoccupied goes down, or out, actually, you charge less because there's less demand. So does that make sense?
The weeks unoccupied, is that right?
Yeah.
Yeah.
So So in the data here, we had what's called a categorical value. So location quality, just separating the high, medium, low. But the problem is sklearn doesn't work with strings very well. So, and especially for linear regression, well, it just doesn't work if you're dealing with these values here somehow.
And that TSV you're talking about, was that the whole thing, or was that just your training set?
It's the whole thing.
Okay.
Yeah, so 100 rows, not big data. Right, so now we're going to convert basic location quality into what are called dummy variables. So Pandas has a really nice formula called get dummies. This will basically create a binary output for categorical values. So high, medium, low, medium, whatever. Alphabetical order. But as you can see, in this case, this is a medium, this is a medium, this is a high, low. Does that make sense, everybody? So now you have something you can predict on. So, any questions here so far?
Aren't you supposed to use, if you have 3 dummy variables, aren't you only supposed to use 2?
Yeah. Yeah. So, if I do this. Right, so it'd be these. So 0 and 0. The general rule, as he points out, and we'll get to this in the example, but if you're doing categorical data in a linear model, you want to drop one of the columns. There's not really a fast rule of thumb. Some of it's based upon frequency. Other people just drop whatever they want to drop.
But essentially, it's that those 2 dimensions, low and medium, completely predict the high dimension.
Yeah, right.
And so by adding that extra dimension, you're just confusing yourself, just like adding color in on chair.
Bingo, right. So it just gives you another opportunity to overfit your data. So let's look at the categoricals real quick before we continue. So in this case, you got 0 and 1 scores against revenue. So I think this highlights sort of what I was discussing earlier, where you have in the fake data, mind you, situations where you have a high impression area where you're charging, medium prices and borderline low prices, right? So obviously a tricky issue, and so we'll. So we're going to split into training tests. I'm going to randomize the indices and the kind of data frame, and then drop the high feature along with the label because we want to get the data. Get column names, and then create a training and test set here with the top 70% for your training and 30% for your test. Is that clear? So, and then fun part, machine learning. It all boils down to this. This is what I mean. It's pretty underwhelming. So we're going to get a linear regression model from sklearn. Who's played with sklearn? Scikit-learn? A bunch of people. Who said they did machine learning? I'm just trying to compare the numbers. Okay. We're sandbagging. Okay, so the basic paradigm is fit, predict, and test, right? So we have a linear regression model here. We're going to fit that model against the training data and the training label. Next, this is more for illustrative purposes, so we've done here. We're going to predict on the test data set. And then we're going to assess the accuracy of the model. So, sorry, Dave.
No, you're all right.
Okay. So, sklearn is pretty cool. I'll just go into it quick. tangent for 5 seconds on this. Scikit-learn is great because it provides you with built-in methods on any estimator that you want to use, estimator being a model. They provide standard fit, predict, score methods. Each of the scoring methods is particular to the model that you're using. So in this case, linear regression, you typically would assess the goodness of fit of the model using R squared, coefficient of determination. It doesn't use adjusted R squared, but it's a good start, and that's all we're going after right now. So it also provides you with predicted values. So if I hit the prediction, it'll actually give me these values for the test data set that I typed in. So does that make sense to everybody so far? And then just coefficients for your model. So everyone remember the slope of the equation for a line? Like it's mx plus b. So I mean, this is basically it. These are just all your slope parameters. So that's basically it. This gives you a good basis to have a model that you can go back to and start testing against the real world. So it's a very simple model, but I chose this model because it's a bit more approachable. So
the scikit-learn is really cool, like you said, because you could also just like go in and switch it out for new.
Yeah, exactly, right.
Like you got linear regression, like okay, well now let's try out this other mathematical formula.
Yeah, it literally
it's
is.
important to know the math and have an understanding because the hacking skills make it so easy to apply really bad statistics.
That's exactly it. And so it's good. It doesn't necessarily do a good job at saving you from yourself. So
How to lie to yourself with statistics.
yeah. One of my favorite books is How to Lie with Statistics. If you ever get a chance to read it, you should. So, but yeah, Dylan's absolutely right. So I mean, they provide a whole suite of linear models. Some which provide numerical output, some which are more like classification algorithms. But I mean, you can go nuts with sklearn. Yeah.
So I am curious about one thing with that data set.
Okay.
You know, you at the beginning you described there was the high, medium, and low that didn't always seem to match up with the data. Did high, medium, and low actually end up being useful in any way? Or was that actually just something subjective that people had developed over time that ended up being kind of wrong?
That's just it, right? So yeah, we'll get to that in a second. It was an internal measurement. So basically, it's like, yeah, we like this area because it supposedly has high traffic and it's I-15. So, and this is, I'm gonna get to this in a second because it highlights a good point. So, okay, so what would the next steps be for this? Well, you can do a deeper dive into the statistics of the data and the output of the model. So, one thing you could do, there's a really good library called Stats Models. I don't know if you all checked it out, but it's phenomenal. So you could look at confidence intervals of the predictions. You could look at p-values, whatever you want to do. It's really up to you. You also want to see how your model actually compares against the real world. Again, back to the lending example. It takes like 90 days to really figure out if your model is going to work or not, which is a long time to wait. In this case, you could almost start plugging in data into the model. We have a billboard in the medium frequency area with this number of impressions. How much do you think we should charge for it? And then go see if that works. I mean, really, it's what the market will bear, though. So. Look at the data source. Location quality was iffy, right? To your point. It's a subjective measurement. And so maybe their designation is just wrong. That could be the case.
To me, that sounds like something that's not, it's not an orthogonal measurement. It's already it's
Yeah.
a convolution of other measurements.
Yeah. Yeah, and I massaged the data a bit to reflect that, right? So because it's based upon, a key measurement being impressions for an area in traffic. So I mean, it is inherently baked into it. I mean, there's a range, but I think the data even showed it was like 80-something% correlated with the revenue. But you can go deeper into what else is correlated with. So yeah, I mean, you want to question your data too. Once you get a model back like this, you're like, well, is location quality even something we want to be looking at or care about? Is it baked in? So, and then, again, use your forecast and actuals to keep adjusting. and adjust and adjust. It's just very much like a rinse and repeat thing. Like I said, I get to see a time where you make one model and you're just great to go for the rest of your life. It doesn't happen. So again, fit, predict, assess, rinse, repeat, rinse, repeat. And so taking a detour really towards the end of this discussion, what technology infrastructure can you use to implement this in your business? So some questions you want to probably ask is, storing the data, analyzing the results. So a setting. So, there'll be multiple consumers of your data, whether it's an actual customer or internal BI. So you've got to take these into consideration. Dylan and I are facing this right now. We're setting up analytics infrastructure for our workplace, and it's questions every day. And the key issues that I need to remind you what technical debt looks like. So you want to figure this out first, because the fun part's the algorithms. The real work is all this stuff. I think that's one of the main points of the discussion there. In Python, lots of machine learning framework options. So you can read the list. You start getting the more larger data sets. Spark's dope. So, and it works. They even have PySpark, so you can write in Python syntax. And there's a link here for. So where is machine learning going? There's, I guess, the data keeps increasing in the world every day. Number of data scientists isn't really keeping pace to address that. You're starting to see a lot of companies doing automated data as a scientist tools. I think I probably see a new one every day. So Amazon released theirs for AWS, Amazon Machine Learning. Google Prediction's been out forever. It's actually really good. You got companies like Ziff down the street that are starting up that are trying to do data science in a box. And you're seeing just this trend that addresses the issues of shortage of data scientists and growing data. And I think ultimately what you're going to see is machine learning and predictive analytics being really a plug-and-play solution. So that's something to consider for your business, because the chance of you hiring a data scientist is going to be pretty slim. Kudos to you if you can, but if you can't, consider these black box options. They might be worth checking out. The problem one of the challenges you might run into is proprietary algorithms or uses of an algorithm. So you need to be able to explain, how that works. And so if you have a black box, then it becomes a bit more difficult. So that's one thing to keep in mind for your IP. So yeah.
I think most people in here too, when you look at that Venn diagram, we definitely have hacking skills because that's why we're all here.
Yeah.
We can go into a business and figure out domain skill, and we can just learn about billboards. But when you get a black box, the black box is automating a lot of that math we don't understand.
Yep.
And so knowing that you're weak in that, be really careful when you actually go. It's fun to apply things and see how it comes out. Before you say this is the answer, give it another go over.
Yeah, Seth actually turned me on to an article. Was it a couple weeks ago? There was somebody at MIT posted some research where they were able to basically come up with an automated data science algorithm. They beat like 2/3 of Kaggle or something like that. It was pretty amazing. So we're not just talking, coming up with a better algorithm. It was figuring out what was useful and automating it all the way to a prediction. So, that in my opinion, that's where it's all going. Because when you look at the business cases too, it's like it's great that you have data scientists and all that, but business people need results and need answers. And if you can get a data scientist to do that, terrific. If not, you may have to rely on this. So, again, if you're in a business where it's a bit challenging to do data science, you may want to look at one of these options. Yeah.
And a lot of engineers, I think, the data munching and that process is still it's the biggest chunk of the work, and that part doesn't quite go away. You still have to clean it up before one of these tools can come in and go, okay, now I can figure out which dimensions I care about.
Oh yeah, absolutely. I mean, so you understand the algorithms. How much work have we been doing right now on data?
Yeah.
Right? Just to get it to that point. It's like a death slog. So it's the hard work. So anyway, just wanted to bring these up as options. I mean, this is in my estimation where it's going. Like I said earlier in my slide, I could be wrong. I often am. But was in May, my sister and I played against Watson on the original Jeopardy set. That was humbling. So, and they're opening up Watson as an appliance. IBM is to be used across business. Their goal is to make what AWS is to the cloud. IBM wants to be that for machine learning and for predictive analytics. You just plug and play and go, and that's it. So, yep, exactly. And why did they do that?
So they can predict everything with all the resources that.
Yeah, and bring that weather data in for everything. It's this nice symbiosis. So, anyway, let's open up to a group discussion. Really, I think that there's quite a bit of good discussion here. I mean, can you see possible use cases for machine learning in your businesses now that you have more of a context?
Well, actually, Joe, I was going to ask too.
Sorry, you want me to go back?
No,
Oh,
this
okay.
is fine. But you're talking about the rinse and repeat cycle.
Yeah.
And a lot of times in those models, you get stuff that doesn't converge, right? And what do you usually do at that point? Do you kind of?
It doesn't usually converge to.
Yeah, I mean, you end up with it getting, your predictions aren't,
Oh, it happens all the time. Yeah, I mean, I think that's been the bulk of, the stuff that, me and my teams have dealt with.
Oh.
And so, you basically, I think, the general framework is, it goes back to understanding your problem and understanding your data. I mean, I can think, there's been several times where we've thought we had a good model and thought we had a good prediction. All of a sudden, it's like, shit, let's get to start over. Because it was, it's either it's overfitted or it just sucks. So, and it sucks because you're just not able to get any signal out of noise, and that's a big part of it. So, so I guess you just go back to the drawing board. I don't know. There's not really so you can tune your parameters and whatnot too. I mean, but I don't know. I mean, it depends. There's a lot of things you could do and not do. So.
Well, just something kind of somewhat related to that black box thing is sometimes you can have a really good model. Oh, it's a neural network that is 100% accurate, but if you can't pull it out and say, oh, we need to improve this because of this location,
right?
Margin more here. It's not descriptive when you know what the future is. So 80% score that you can actually explain.
It's a huge part, right? And I have actually a friend of mine who's a math professor for doing machine learning for 20, 30 years almost now. He doesn't even touch neural networks for that reason, because it's hard to explain the answer. So, and they tend to do a really good job at overfitting. I think deep learning is getting a lot better. But to your point, it's if you can't explain it, then you don't know what to change. So, yeah.
To some extent, this is pure devil's advocate.
Sure.
But so you say you warn against black boxing things.
But then I talked about using a black box.
But yeah, isn't it okay? I mean, just so long as if you really do your job right, you do your split.
I wasn't saying don't use a black box.
And you believe you did, So, and then you think that you trust what your errors are on the basis of, you open the box and then you look to see how you did, right?
Yeah, no, it's a very valid point. So I think it depends on your comfort level, right? So I mean, if you, I think like it or not, the world's moving towards black boxes. So you're just gonna have to get used to it.
Well,
So there's that.
Some of those algorithms are built on certain assumptions, like normality of the data.
Yeah.
And then if you're coming out with like, okay, this is a great answer, but it's completely invalidated and everything because it doesn't make any assumptions. So
Yeah.
you wouldn't get an actual good answer.
Yeah. So.
Do you spend a lot of time quantifying errors? I assume that's part of your reanalysis. And if you do, maybe this is a question that's too broad to be useful, but do you feel like there's sort of a general idea of what you feel like is an error level that is acceptable because you just can't go beyond it because reality is too chaotic or something like that?
It's a tough one to answer.
I mean, you probably want less than 50% error, or it's practically useless to even have a model at all.
I think it just depends on the problem you're trying to solve, frankly. I mean, we've seen issues where, you know, I mean, the whole notion really is to like try and reduce your error, right? So, but I mean, I think it's just, you got to take it on a case-by-case basis. I don't think there's like a one-size-fits-all answer. That's like I'm going to say, like, you know, for linear regression, like, yes, you know, all R squares must be above 80% or something.
I think it is interesting that a lot of these problems you see, like the business side, people don't deal with individual errors. Like, there's no errors on that price value. You have a price of what this billboard was, right? And you could view it like a height of a person or a person's t-shirt size. You could, like, how wide around. But the big data question is people aren't propagating errors. Like, you don't take an error in somebody's shirt size and then propagate that through your model. And it is interesting, I think, in sort of a data quality sense.
Even to get to that point, you have to have you have to know your model and data really, really well in order to even get any value out of error propagation. I think I probably would say, like, I don't know, it's like 3% error.
The error is built in, right? Or, I mean, because you have those scatter plots.
Well, if you have statistical error, you don't know what your
But I mean, so there was the width, right? As you plotted those lines, and so you can talk. Yeah, there's that price was exactly what it was. So there's in some sense zero error, but from in a deeper sense, there's still that scatter as you run up in impressions.
Yeah, exactly. So
That's the big difference. You have lots of these individual points, and then you can say something about the distribution. And those distributions are
one more than first give me the evil eye.
So just one thought that I had that I kind of had a tough time with on the billboard example.
Yeah.
For instance, I mean, it looks like the data was aggregated over a certain amount of time, obviously.
Yeah.
But and the overall theme of what we're trying to do here is fit essentially a supply-demand curve.
Yeah.
To the billboards based off of impressions and that. But what the data didn't show was there any group deals where you could buy 5 billboards at a discounted
Correct.
price, or was there any sort of incentives to to pick up some of these lower
Right.
So and what we know about people, especially folks like marketing people or folks like salespeople that are commission based, is they're going to keep on changing their strategy over time. And that's going to impact the fitability of your model, and I suspect that's where your iterative process of fitting that is going to come in, because then you can kind of adapt to that.
So the next question would be, okay, so how do we factor in discounts?
Yeah.
Right. So do you have that data? And so the data they provided was the data they said they had. So now you have to go back and say, well, okay, so now is there anything else we should be aware of? So, I mean, that's basically it. I mean, it's very valid. So. Cool. Reis, yeah. Cool. That's it. Thanks. Need a projector?
No, I don't think so. Another round of applause for Joe, guys. Sweet. So this is everybody's second favorite part, other than the talk, right? This is the raffle, and because we're doing a Zaniac raffle, what I'd like to ask is if you or someone you know is between the ages of 5 and 12. Then take your name tag and fold it in half, and you're able to drive here or in one of our schools that we have like the van for. Take that, fold it in half, and you can get yourself entered for this gift certificate. Sure. So, I'm just gonna pass this guy around.
Appreciate it. Interesting. This happens. This group here.
Is that everybody who wants to enter for this one? You'll automatically be entered for the next one. And by magic, I mean I'm just going to leave your name in. Cool. Hey, Joe, did you enter?
No, but I should my boy turns 5 in a couple days.
Can you read?
Yeah.
Oh, okay. I was going to have you draw if you weren't entering.
Oh, well, I'll draw.
No, enter. David, you draw. You're our guest of honor from way up north.
The great boy.
So the winner of the gift certificate is
Ryan Sollers.
Ryan. Woo! Cool. So everybody else who wants to enter for this awesome book from Microsoft Press, Code, Hidden Language of Computer Hardware and Software. It's actually pretty good. I got myself a copy. Who's read Gödel Escher Bach, by the way? Yeah. It has some, it's like the lighter version of Gödel Escher Bach. It's pretty good.
Just enjoy Django. It's interesting to see how the presentations fit against the group. Your presentation will be fascinating.
Yeah, pass it down.
Understand the level of detail, but I guarantee most of them here did. You know what I'm saying? It's really bizarre.
Does that everybody want to enter? I got one more over here. So, winner of the book? Oh. Okay, last call. Going once, going twice.
Right here. Oh, sorry. That was Gavin. Your odds just went down.
Yeah, right?
I won't feel bad if I win.
David Ernst. No, I'm just kidding.
Elizabeth Frost.
Elizabeth.
So we went to
Oh, and we also have goodies from Dealer Track.
a couple weeks ago.
I left my jacket.
Oh,
Yeah. I was like,
yes. So, follow the thumb drive. No, I'll head these out one at a time. These are thumb drives. There's thumb drive type clips, I think.
8 gigs, I believe.